And nowadays, machine learning people say that data is all you need. So if you just simulate long enough, you can get capable policy. Yeah, so that's all. Thank you.
Thank you. I'll welcome the 4 speakers back up to the stage so we can start our question answering session. So just remind you, if you have a question, we've got mic runners and we need to use the mics for the online presence as well. Great. Let me go ahead and take it. Good question.
So to Maximilian, so you have your lane level route planning, and it accounts for things like you mentioned lane changes and forced lane changes, which I presume would be things like the space might be a little tight, but we're going to switch into that lane anyway because we don't have a choice. And you tried to penalize that. And so you get what I'll call what I think is a static route plan so that you can get from one location to another location. What if things dynamically change, like a lane closes or there's a collision or ducks are crossing the street and now your plan no longer holds and you can't even do a forced lane change? It's just not open. Then what happens?
Yeah, so the policy is static in the sense of you compute it once for a goal, and then it covers the entire area that you might be driving in, but it doesn't prescribe. It doesn't necessarily prescribe, right? It takes into account to an extent the stochasticity of, I might not be able to do a lane change. So if for some reason I don't get to lane change, that is baked into the policy. What wouldn't be baked in is, yes, if something changes on a more fundamental level. So like you said, for example, a road completely closes or something to that extent, then you would have to run the routing algorithm again with that new information of actually this road is closed. But in terms of does a dog cross the road or is there traffic around us? That problem is more low level and is handed off to whatever motion planning framework is driving your car. And the router tries to take into account those variabilities, at least with respect to lane changes. And that is why that stochasticity is baked into the router formulation and ultimately the policy.
Yeah. Any other questions for our speakers? Thanks.
I have a question for Kong. So, very nice work. Thank you for your presentation. I was wondering, you mentioned that those drift cams will communicate with acoustic transponders, right? So given that acoustic signals have very limited communication bandwidth, have you thought that you may have some problems with acoustic communications? And if yes, because this is going to be a decentralized method, what are the communication requirements for your methodology to work?
Let me rephrase it to see if I understand the question. So are you asking about the requirement of the communication?
There are basically 2 questions. The first question is, what are the communication requirements? And if they're heavy or like high, how do you plan to address that problem, given that acoustic communications have very limited bandwidth?
Okay. The communication requirement now depends on the task. So basically, because the control is only a part of our research, and another very important thing is how can they estimate the flow field, the environment, and to do that, they just need to, because the drift cam, they just drifted with the flow horizontally. So what they need is they need to detect the motion of at least their immediate neighbors. So that is not an active communication. It's kind of a passive. And other than that, if you have the estimation of the flow and you have control, then what you need to do depends on your goal. For example, here we want to observe the motion of the scattering layer. So then I think we, to capture the density of organisms, we need at least some reciprocal communication. So that depends on the task. Yeah.
Cool. Thank you.
Mhm.
Do we have any other questions? Great. I was looking for the other side of the room, so the mic runner out that side.
There's a question for Saurav. You said that you had no theoretical guarantees of your performance for the greedy algorithm. Is your objective function in that problem, have you checked if it's submodular at all?
So we do not make an assumption that the objective function needs to be submodular, but for specific kinds of function, for reward functions, it might so happen that the objective function is submodular, and in those cases, it might be easier to prove a guarantee, but we haven't worked on that yet. I'm aware of approximation algorithms for submodular functions, but over here in the formulation, we do not make any assumption as such for the rewards.
Yeah, go ahead.
Very quickly, you said you proposed the NemIQP formulation. Was the cost quadratic and convex or not convex?
Sorry, I didn't catch the question.
You said you proposed the NemIQP formulation for the problem,
Yes.
right? Was the cost convex or not convex? Just to understand.
So I'm not sure if the cost is convex or not. It's definitely quadratic, but that's something that we need to analyze whether there's convexity in the function or not.
Okay, thank you. Thank you very much.
Can you raise your hand again? Perfect.
Hi, I have a question for Zhao Ming. Thank you for your talk. So when you train the reinforcement learning algorithm on the simplified model, what are the details involved in transferring that policy to a more complicated robot? Because that seemed to be a really important step.
Yes.
So yeah.
Yes. So as I mentioned in the presentation, so the policy in the central model will eventually give us the ground reaction forces for the stance foot. And you can transform that into joint torque for the stance foot using Jacobian transpose. And then for the swing foot, we have the central model give us the desired position of the swing foot. And then we can come up with a Bezier curve connecting the current foot position to the desired foot position and then do position checking for the swing foot. Does that answer the question?
Yep. Thank you.
Thank you.
Yeah, I had a question on the lane change paper. Yeah. So you presented 3 properties that you wanted of the density function, right? I definitely understood the first 2, but in the third one, you were saying essentially on a lane of length L1 plus L2, you had failure on L1 and then success on L2. But that seemed to be you're assuming some independence on those 2 segments, which maybe doesn't really model the true system. Isn't that true? I'm just thinking if you're driving and there's a car driving beside you and you fail in a lane change, then if you try again a little bit later and the car is still beside you, they're correlated events.
Right. I'm actually super happy you asked this because there was a point that I just realized I forgot to mention in the presentation. The reason for that constraint is that we would like the model to be independent of whatever the size of the cell that we subdivided in. So if we subdivide smaller, then we don't want the model to change. But yes, that's a good point. I wonder if that, I'm not 100% sure. I'd have to think about it, but that's a good point. We do assume them to be independent. I'm not sure if that actually changes much. But yeah, the reason for that particular constraint is so that our model of lane change success is independent of whatever size we subdivide the cells in. I guess you could do something where it's not quite that function. It's something that is basically, if I failed previously, then I'm more likely to also fail in the future. You could probably come up with a function that does that. But at that point, I guess you're tuning, right? You also need to determine, well, how correlated are these things? But it's an interesting idea. I haven't thought about that.
Okay, thank you.
Any other questions? Great.
Yeah, I want to ask Jiao Ming. So yeah, I want to know more about what is the state in the agent. I'm pretty sure that it's not images, but I don't know what you use to train the agent, because like as human, I kind of need to see the whole the road ahead, to kind of plan where to put the foot in or something like that. So I don't know, like if you have, you can describe the state in the agent. So
Okay, can you repeat the question? I didn't quite catch that. Sorry.
Sorry?
Can you repeat the question?
Yeah, I want to know more about what is the state in the agent. Like what kind of thing that you use to be the state for training the agent?
So you mean the input to the policy?
Yeah.
Yes. So the input to the policy will be the state of the rigid body. This means the linear position, linear velocity, orientation, and angular velocity of the rigid body. We also know the foot position with respect to the rigid body. So like where the foot is currently as input to the policy.
But I mean, how can the agent kind of know where to put the foot on? Because like if a human kind of walk in a uneven surface, right? We kind of need to kind of see the surface.
Oh,
like,
you mean the terrain? Okay. Yes.
Yeah.
So for the terrain, we have a height map on the terrain. So I believe it's 1 by 1 height map around the center of the robot. And it's only used for swing foot control. So for example, for the stepping stone terrain, first we use the Weber heuristic to decide where we should put our foot. But for example, in the stepping stone terrain, not all footholds are feasible. If the Weber heuristic, we choose a foothold that's not feasible, then we will choose the closest point on feasible terrain. So we will choose a point on the feasible terrain that is closest to the Weber heuristic, and then we will choose that as the foothold. For the stance foot control, we didn't consider the terrain, so we just know where the foot is with respect to ours, the body. Yeah. Great.
That's great. Did that answer your question? Thanks. I think we have a question over here.
This question is also for you, Xiaoming. I didn't completely understand why does the centroidal model made reward design simpler. So how does this work, and what is your intuition on how this could be extended to other robotics applications?
Yeah, so the centroidal model is simpler because it just has one single rigid body that we need to regularize. While in the full-order model, you also need to worry about, you don't want the joint velocity to be too large so that you get some jittery behavior, etc. So you need to regularize a lot of behaviors like joint jittering and also high foot impact, etc. While in the centroidal model, you only need to worry about one single rigid body. That's why it's much simpler to design a reward function. And what's the second part of the question?
Yeah, the second part was, what's your intuition on how this could be extended to other robotics applications? And my question is going to the side that, doesn't this replace reward engineering by some sort of state engineering?
Yeah, so here we basically borrow intuition from model-based control community, so that because they find that this potato model can already can do a lot of agile locomotion on their quadrupedal robot, and we directly borrow that. But eventually it will be limiting because it's still